Hello, friends! The double-slit experiment has its roots in the early 19th century when Thomas Young, an English polymath, sought to explore the nature of light. At that time, the dominant theory suggested that light was composed of particles. However, Young's curiosity led him to propose a different idea, that light could also behave as a wave. To test this, he designed an experiment that would forever change our understanding of the physical world. Young's setup was remarkably simple, yet incredibly insightful. He used a coherent light source, which could be a lamp or a more sophisticated laser in modern renditions, to shine light onto a barrier with two closely spaced slits. Behind the barrier, he placed a screen to capture the light that passed through the slits. Young's expectation was that if light were purely a particle, it would simply create two bright spots on the screen corresponding to the slits. Instead, what he observed was an interference pattern, a series of bright and dark bands, indicating that light was behaving as a wave, with peaks and troughs interfering constructively and destructively. The implications of Young's findings were profound. His experiment demonstrated that light exhibits wave-like properties, a concept that was revolutionary at the time. This wave theory of light suggested that light could bend, spread out, and interfere with itself, much like waves on water. This discovery was a critical milestone in the field of optics and laid the groundwork for the development of wave theory in physics. As scientists delved deeper into the nature of light, they began to uncover even more perplexing behaviors. It wasn't until the 20th century, with the advent of quantum mechanics, that the true complexity of the double-slit experiment became apparent. Researchers found that when individual photons, the fundamental particles of light, were sent through the slits one at a time, they still produced an interference pattern over time. This suggested that each photon was somehow interfering with itself, a phenomenon that defied classical explanations and hinted at the bizarre nature of quantum mechanics. The double-slit experiment's setup may appear simple, but the underlying principles it reveals are anything but. To understand the experiment, let's break down the key components and the observations that have baffled scientists for decades. When a coherent light source, such as a laser, shines on a barrier with two slits, the light waves passing through each slit spread out and overlap. This overlapping creates an interference pattern on the screen behind the barrier. Bright bands, or fringes, appear where the waves from the two slits constructively interfere, that is, where their peaks align. Conversely, dark bands form where the waves destructively interfere, canceling each other out. This interference pattern is a hallmark of wave behavior, demonstrating that light, under these conditions, acts as a wave. However, the experiment takes a quantum twist when individual photons are introduced. When photons are fired one at a time through the slits, they still produce an interference pattern on the screen, even though there are no other photons to interfere with. This suggests that each photon behaves as a wave, passing through both slits simultaneously and interfering with itself. To further explore this phenomenon, scientists have used detectors to observe which slit a photon passes through. Remarkably, the mere act of observation alters the outcome. When detectors are placed at the slits, the interference pattern disappears and photons behave like particles, creating two distinct spots on the screen. This peculiar effect, known as the observer effect, highlights the fundamental role of measurement in quantum mechanics. The double-slit experiment is a cornerstone of quantum mechanics, illustrating the wave-particle duality of light and matter. Wave-particle duality is the concept that particles such as photons and electrons exhibit both wave-like and particle-like properties depending on how they are observed. This duality is one of the central mysteries of quantum mechanics and has far-reaching implications for our understanding of the universe. One of the most intriguing aspects of the double-slit experiment is the concept of superposition. Superposition refers to the ability of quantum particles to exist in multiple states simultaneously. In the context of the double-slit experiment, a photon in superposition can pass through both slits at the same time and interfere with itself. This idea defies classical logic and challenges our intuitive understanding of reality. Another fascinating implication of the double-slit experiment is quantum entanglement. Entanglement occurs when two or more particles become linked in such a way that the state of one particle is dependent on the state of another, regardless of the distance between them. In some versions of the double-slit experiment, entangled particles are used to demonstrate non-local effects, where the measurement of one particle instantaneously affects the state of its entangled partner. The double-slit experiment also raises questions about the nature of reality and the role of the observer. The observer effect, where the act of measurement alters the outcome, suggests that reality at the quantum level is not fixed but is influenced by observation. This leads to philosophical debates about the nature of existence and the role of consciousness in shaping reality. After the success of the double-slit experiment with light, scientists wondered if other particles would show similar wave-like behavior. Electrons were the next to be tested. When electrons were fired one at a time through the double slits, they still created an interference pattern on the screen. This showed that electrons also exhibit wave-particle duality, behaving both as particles and waves. This was a groundbreaking discovery, proving that not just light but all matter has wave-like properties. Neutrons, which are even more massive than electrons, were the next candidates for the double-slit experiment. When neutrons were used, they too formed an interference pattern. This demonstrated that wave-particle duality applies to particles with more mass as well. These experiments with neutrons further solidified the idea that all particles, regardless of their size, can exhibit wave-like behavior under certain conditions. One of the most astonishing versions of the double-slit experiment involves large molecules, such as buckyballs, carbon-60 molecules. These molecules are composed of 60 carbon atoms, making them significantly larger and more complex than electrons or neutrons. When these large molecules were sent through the double slits, they still produced an interference pattern. This surprising result showed that even large, complex molecules can exhibit wave-particle duality. It challenged our understanding of the boundary between classical and quantum physics, suggesting that wave-like behavior can extend to much larger scales than previously thought. As we delve deeper into the double-slit experiment, we encounter even more advanced concepts that challenge our understanding of the universe. One such concept is the wave function, a mathematical description of the quantum state of a particle. The wave function encapsulates all the possible states a particle can be in and provides probabilities for each state. When a measurement is made, the wave function collapses to a single state, a process that remains one of the great mysteries of quantum mechanics. Another advanced topic is the measurement problem, which questions how and why the act of measurement causes the wave function to collapse. Various interpretations of quantum mechanics attempt to explain this, including the Copenhagen interpretation, which posits that the wave function collapse is a fundamental aspect of nature, and the many worlds interpretation, which suggests that all possible outcomes of a quantum measurement occur in separate, parallel universes. The double-slit experiment also plays a crucial role in the development of quantum field theory, a framework that combines quantum mechanics with special relativity. Quantum field theory describes how particles interact with fields, such as the electromagnetic field, and has led to the discovery of many fundamental particles and forces. Quantum mechanics has found surprising applications in biology, particularly in understanding how living organisms function at the molecular level. One example is photosynthesis, the process by which plants convert sunlight into energy. Researchers have discovered that quantum coherence helps plants transfer energy with high efficiency. This means that light particles, photons, travel through the plant's cells in a wave-like manner, allowing them to find the most efficient path for energy transfer. This insight is helping scientists develop new, more efficient solar energy technologies. Another fascinating area is quantum biology, which explores how quantum mechanics influences biological processes like enzyme reactions and even bird navigation. Some birds are believed to use quantum entanglement in their eyes to sense the Earth's magnetic field, helping them navigate during long migrations. Quantum mechanics is fundamental to chemistry, as it explains how atoms and molecules interact. The behavior of electrons within atoms is governed by quantum principles, which determine how atoms bond to form molecules. Quantum chemistry uses these principles to predict the structure, properties, and reactions of molecules, enabling chemists to design new materials and drugs. One significant application is in the development of quantum computers, which have the potential to revolutionize chemistry. Quantum computers can simulate complex chemical reactions at the quantum level, something that classical computers struggle to do. This capability could lead to breakthroughs in drug discovery, material science, and industrial processes. In cosmology, quantum mechanics plays a crucial role in understanding the early universe and the fundamental nature of space and time. Quantum mechanics and general relativity are the two pillars of modern physics, but they are often in conflict. Researchers are working on theories of quantum gravity to unify these two frameworks, aiming to explain phenomena such as black holes and the Big Bang. One area where quantum mechanics intersects with cosmology is in the study of cosmic inflation, a theory that explains the rapid expansion of the universe just after the Big Bang. Quantum fluctuations during this period are believed to have seeded the large-scale structure of the universe, leading to the formation of galaxies and other cosmic features we observe today. The principles of quantum mechanics are influencing many other fields of science as well. For example, in neuroscience, researchers are exploring whether quantum effects could play a role in brain function and consciousness. In material science, quantum mechanics is essential for developing new technologies like superconductors, which can conduct electricity with zero resistance at very low temperatures. Overall, quantum mechanics is not just a theory confined to physics. It is a powerful framework that is driving advancements across various scientific disciplines. By understanding and harnessing quantum principles, scientists are unlocking new possibilities and gaining deeper insights into the natural world. The double-slit experiment fundamentally challenges our understanding of reality. When particles like photons or electrons are not observed, they seem to exist in a state of superposition, meaning they can be in multiple places at once. However, when we observe them, they appear to choose a single position. This suggests that reality at the quantum level is not fixed, but probabilistic. The act of observation appears to play a role in determining the state of these particles, leading to the question, does reality exist independently of our observations, or do we create reality through the act of observing it? The idea that observation can influence the outcome of quantum events raises questions about free will. If our observations can change the behavior of particles, it suggests that our choices and actions might influence reality at a fundamental level. This leads to philosophical debates about whether free will truly exists or if our sense of making choices is just an illusion. If reality is influenced by observation, Do we have control over our observations, or are they predetermined by some underlying quantum processes? One of the most intriguing questions raised by the double-slit experiment is the role of consciousness. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the observer's consciousness causes the wave function to collapse, determining the state of a particle. This idea implies that consciousness plays a fundamental role in shaping reality. However, this is a highly debated and controversial topic. Critics argue that it is not consciousness, but rather any interaction with a measuring device that causes the collapse. Despite this, the experiment continues to fuel discussions about the connection between consciousness and the physical world. Another philosophical implication of the double-slit experiment is the many worlds interpretation. This theory suggests that all possible outcomes of a quantum event actually occur, but in separate parallel universes. According to this interpretation, when a particle passes through the double slits, it takes every possible path, creating a branching universe for each possibility. This raises questions about the nature of reality and our place within a potentially infinite multiverse. If all possible outcomes exist, what does that mean for our sense of identity and existence? The observer effect in the double-slit experiment also leads to questions about the nature of measurement and reality. If the act of measuring something changes its state, what does that say about the objects we measure and our methods of measuring them? It challenges the idea of objective reality and suggests that what we consider to be real is deeply intertwined with how we observe and measure it. Classical physics is based on determinism, the idea that given enough information, we can predict the future state of any system. However, the probabilistic nature of quantum mechanics challenges this view. The double-slit experiment shows that we can only predict the probability of a particle's position, not its exact location. This shift from determinism to probabilism raises questions about the predictability of the universe and whether true randomness exists. These philosophical questions raised by the double-slit experiment continue to inspire debate and exploration. They push us to rethink our understanding of reality, consciousness, and the nature of existence itself. By exploring these ideas, we gain a deeper appreciation for the mysteries of the quantum world and the profound implications it has for our understanding of the universe. The double-slit experiment's principles are fundamental in understanding how lasers work. A laser produces coherent light, meaning all the light waves are in phase and have a single wavelength. This coherence is crucial for the interference patterns seen in the double-slit experiment. Lasers are used in various applications, from medical surgeries to cutting materials, and even in everyday devices like barcode scanners and laser pointers. Quantum computing relies heavily on the principles demonstrated by the double-slit experiment, particularly superposition and entanglement. In a classical computer, bits can be either 0 or 1. However, in a quantum computer, qubits can be in a state of 0, 1, or both simultaneously, thanks to superposition. This allows quantum computers to process vast amounts of information much faster than classical computers. Entanglement enables qubits that are entangled to be interconnected, so the state of one qubit can instantly affect another, regardless of the distance between them. These principles allow quantum computers to solve complex problems that are currently impossible for classical computers. Quantum cryptography uses the principles of quantum mechanics to create secure communication methods. One such method is quantum key distribution, QKD, which ensures that any attempt to eavesdrop on the communication changes the state of the quantum particles involved, thus alerting the communicating parties to the presence of an intruder. This level of security is based on the observer effect seen in the double-slit experiment, where observing a quantum state alters it. By leveraging this property, Quantum cryptography can potentially provide unbreakable encryption, making data transmission secure against any hacking attempts. These applications showcase how the principles uncovered by the double-slit experiment have revolutionized technology, leading to advancements that impact our daily lives and future technological developments. Thank you for joining us on this journey on quantum experiment. Please like, comment, and share the video, and please do not forget to subscribe for more videos.